In this video, we're going to take that five-step guideline process that we talked about in the last video and apply it to a couple of molecules to show you how this can work. So let's look at this molecule, formaldehyde, and let's draw the Lewis structure of H2CO. Okay, step one is how many valence electrons do we have? All right, so a periodic table can be really helpful as you're doing this. You also start to get to know some of these as you get practice with these different molecules. So hydrogen's the easiest one. So we have two hydrogen atoms because of the subscript here. So 2 times 1 electron per hydrogen atom. One carbon that has 4 valence electrons. Again, double check me on the periodic table, but you have two 2s electrons and 2p electrons. And then oxygen has 6 valence electrons. Again, it has 2 more electrons than carbon, so it has a total of 6 valence electrons. Okay, so if we add all those up, we get 2 plus 4 is 6, plus 6 is 12 total electrons. Right, that's useful to know at the beginning of the problem as we continue with the rest of it. Okay, now how do all these atoms fit together? You can sort of draw a rough structure and then start filling in. Hydrogen will never be in the middle of a molecule because it can only form one bond. And so then the next thing listed after hydrogen, and in this structure is written in the way it is to indicate that the hydrogens are bonded to the carbon and the oxygen is also bonded to the carbon. So we'll write carbon in the middle and oxygen on the top, and I draw them at slight angles like this, but if you draw it sort of like at right angles, it doesn't matter at this point. We're not indicating geometry with Lewis structures, just how the molecules are, how the atoms are combined and sharing electrons. Okay, so that's step 2. We have drawn our molecule with single bonds between everything. Another guideline you can use is that carbon can form the most bonds out of the atoms that we have, because it can form up to 4 bonds because it has 4 single unpaired electrons that need to be paired up. And so that will also be a good indication of what's generally in the middle of the molecules, whichever one can form the most bonds. And if there's carbon, it's probably going to be in the middle. Okay, so we formed all of our bonds. Okay, so step 3, we need to make octets on the outer atoms. Hydrogens are good already because they just need that one shared bonding pair of electrons, so that's good. And then oxygen, since it has one bond, we're going to need to add 6 electrons to form that. Okay. And for now, we ignore the central atom. All right, let me just erase some of this so I have space to keep doing the next parts here. Okay, we have added all the electrons to the outer atoms. Now, the next step is we recount the number of total valence electrons and see if we've added enough electrons. All right, so we need a total of 12 electrons. So we have 2 for each of these, 2 for each of these. So that's a total of 12 electrons. 2 plus 2 plus 2 is 6, plus 2 is 8, 10, 12. So we get a total of 12 electrons here. So that matches our total number of electrons. So we don't need to add any more electrons to the structure. We're good. Now, the last step is we need to check, does the central atom have an octet? We formed octets on all the outer atoms, and carbon is lacking. Carbon only has 6 electrons because of its 3 bonds. So it needs another pair of electrons. So I'm just going to draw, we're going to need to share 2 bonds. Hydrogen can't form an extra bond, so we know it can't be the hydrogens. That would give them too many valence electrons. They can only have 2. They have a duet rule rather than octet rule. So instead, we will borrow one of those pairs from oxygen and arrive at this structure. So this is the structure for formaldehyde. And we have the right number of valence electrons. One thing we can always do to double check that we're good is that we have the right total number of valence electrons. We already checked that. And that everything has an octet, or in the case of hydrogen, a duet of electrons. So if we look at the oxygen, we see 2, 4, 6, 8. All right, so that's good. For carbon, 2, 4, 6, 8. And often with carbon, what we're looking for is that it has 4 bonds to it because it has those 4 individual electrons that need to be shared. And then for the hydrogens, as long as they have 1 bond, they're good, and they won't ever have any lone pairs on them. Okay, so that's formaldehyde. Let's do this with one more structure. We'll do one now that, and you may be wondering, what if there is not just one central atom? So we're going to do this molecule right here, acetylene. This is a commonly used fuel for welding torches. So acetylene, we have 2 carbons and 2 hydrogens. All right, so again, the hydrogens are not going to be in the middle. Oh, I got ahead of myself. How many valence electrons? What's our total number of valence electrons? You'll get really used to doing this for carbon and hydrogen because they show up in a lot of different molecules. So carbon has 4 valence electrons. There's 2 of them, and there are 2 hydrogen atoms, which have 1 valence electron each. So we get a total of 10 electrons in this molecule. All right. Now, the next question is, how are we going to arrange these atoms? Again, like I was just saying, hydrogens are not going to be in the middle. If we put a hydrogen in the middle and bond a carbon to it, it can't form any more bonds. It doesn't have any extra electrons left to do that. So we won't put hydrogen in the middle. So we'll start with 1 carbon in the middle, and we can actually bond another carbon to it. And each of those carbons can have a hydrogen attached to it. Now, there's a few different ways we could have done this. What about doing this? So that's a possibility too, right? But the problem is that this carbon is going to need to form more bonds. So it's easier for it to form extra bonds with the other carbon rather than just being off by itself out here. We can try and do it this way after. We'll do the correct way first, but maybe we'll, if the video's not going on too long, maybe I'll show what happens if we try to do it that way. Okay, so we've got the 2 carbons bonded to each other. And sometimes the formula of acetylene is actually written to reflect the fact that the carbons are bonded to each other rather than and the hydrogens are on the ends of the molecule. So you can also write this formula this way to emphasize the structure. Okay, so now let's go ahead and do our outer atoms. Make sure we have enough electrons on them. Well, in this case, we'll just think about the hydrogens. We'll worry about the carbons. We'll consider each carbon a central atom. So we're done with that step. Then the next step is we need to check the number of valence electrons. So we have added 2, 4, 6 electrons in this structure. We need 4 more electrons. Okay, and so this is our first example where we're going to be adding electrons to central atoms. Let's go ahead and add them. We'll add 1 pair to each carbon. We're still not done with this, but that's a good starting point. Okay, we've added 1 pair to each carbon. All right, so now we have the correct number. Now we have 10 electrons. Okay, and now let's check octets. So on our outer atoms, we already know that the hydrogens are okay, so we're good. But our central carbon atoms, if we look at each of them, they both are going to be the same. We have 1 pair here, 1 pair here, 1 pair here, if we're looking at this carbon atom, and that's only 6 electrons. And the same thing is going to be true on this side, that it only has 6 electrons. So we're going to need to share electrons to be able to get the correct number of bonds here. Okay? So, how can we do that? Well, we could share this pair into the middle and form what's called a double bond. We've seen this already in the last couple of examples that we've done. When there are 2 pairs of electrons that are shared, form a double bond. All right. Does that solve all of our problems? Well, not completely. We've shared some electrons, but this carbon still only has 6. But this carbon atom now has 8. So this one's okay, because it has 2 pairs of shared electrons here. There's 4, and then we still have these 4 on the other side in the lone pair and the other single bond. So let's share this pair so that the other carbon can also have 8 electrons. And so our final structure ends up being this, where we have no lone pairs. And this forms what we call a triple bond, where we have 3 pairs of electrons shared between these 2 carbon atoms. All right, and this satisfies all of our requirements. Our hydrogens have 2 electrons around them, and each carbon has an octet. It has that set of 8 electrons with 3 pairs of electrons needing to be shared for this octet to actually form. All right, and so that concludes our initial introduction to Lewis structures. We'll practice with this a lot more in class, and you'll get a lot more practice on your homework as well. But this introduces the basic guidelines that we'll be following to draw Lewis structures for the rest of this chapter.